Good evening everyone. Welcome to the misconceptions in physics. Welcome to, this is the 22nd video on rotation. Let me just share my screen. My name is Ratankar Rao. I teach physics in an international school in Bangalore. Just a minute, okay. Just give me a moment. I have not opened my PPT. Just give me a moment. I'm just opening it. Okay. And my hobby is to teach physics and make videos helping out the student community there. So do share. And I generally like problems which are really challenging enough for me and for the students, and try to solve such problems. Problem solving in physics is really a wonderful thing. Okay, so enough of my story. And now let us see the problem. So we are now looking at the rotation. And if you want to see all my videos so far, which has been recorded, you can visit my website, which is at ratankar.com. Okay. Now what we'll do is, let us start solving it. Okay. So the problem reads, finding speed of the center of mass during an impulse. Okay. So the problem reads like this: a uniform rod of length L lies on a smooth horizontal table. So you have a smooth horizontal table on which a uniform rod of length L and mass M lies on it. A particle moving on the table strikes the rod perpendicular. I do one thing. Let me just change it. I don't want to have it like this. Just give me a moment. I need a bigger diagram. So this will not be sufficient for me. Okay. Yeah. So you have a uniform rod of length L, mass M, lies on a frictionless table, which means mu equal to 0. Okay. So that means if you touch it, the object keeps on moving. Right. Now, a particle of mass M, there is a mass M, I missed it. A particle of mass M, this mass is M, small m, this capital M. Moving on the table, strikes the rod perpendicular at an end and stops. It comes, it hits it over here. Remember, it's not been hinged anywhere over here. Okay, and then it stops. Find the distance traveled by the center of the rod by the time it turns to a right angle triangle, right angle. This answer is not pi L by 2, it is pi L by 4. Make this change. Okay. Now, what is the student response? So student thinks that the moment this hits over here, this is center of mass of the rod. When it says find the distance traveled by the center of the rod, by the time it turns to a right angle. So what will happen is, this rod, he assumes that it moves like this. And it becomes like this over here. It becomes like this. So that the angle here is pi by 2. And as a result of this, now we can say that the distance traveled, distance described by the center of the rod is nothing but S equal to R theta. So what does it do here? R, what is R here? This distance, which is L by 2, multiplied by, what is the angle described? Pi by 2. And hence the answer should have been pi by pi L pi divided by 4. So this is what is the answer. Most of the students have written it like this. Okay. And this is a misconception. Now, why is this a misconception? The reason is because when you have an object and you describe something like this, that means you are assuming that this part of the rod is being hinged. And as a result of it, there's a pure rotation takes place. So when there is a pure rotation, I agree, whatever you have done is correct. But here, the story is a bit different. Let me tell you how it is different. When this particle comes and hits it, this particle remains here itself. Okay, it comes to rest. That's what according to the question is given. And hence all its kinetic energy, what it had while it moves, has been transferred to this. Now, as a result of it, what will happen to the rod? The rod will now start moving. Now, since it has not been hinged here, so this part of the rod will also move. This part of the rod will also move. This will also move. This will also move. Every part of the rod will be moving. But since it has been hitting over here, I can say the center here might move like this. The new position of the rod could be like this over here. Maybe after 1 microsecond, if you see, this could be the new position of the rod. Then the next second, for example, this could be the rod. This could be the rod. Right? See, the center is also moved. This is also moved. This is also moved. Then the next second might be, this could be the rod. And last second might be, this could be the rod. Which means what? Let us say this point is O here. This point O has got displaced by a smaller amount here, which is to O dash O here. And the center of the rod is not describing an arc of a circle like this, but instead it becomes like this and goes over here. Now, but the angle still is 90 degree, definitely. But which means that there is a rotation of the rod and there is also a translation of the rod. When I consider this way, I am just looking only at the rotation part of it. See how nice the problem is, right? So we do not have a translation bit described. I have not considered the translation. That's where the student made a mistake. Every problem in physics, we need to look at a very detailed way. You need to break them, chop them into smaller and smaller and smaller parts so that you understand it correctly. Okay. Now, therefore, this answer is incorrect because you just overlooked the problem. Now, the question is, okay, I understood everything, but now how do I solve it? Right? So let us see now, like, how do we actually come back to the solution? Okay, let us do this. So once again, let me draw the picture. So this is my rod of length L, mass M, then mu equal to 0, a particle of mass M moving with a velocity V, hits it, and as a result of it, it starts rotating. Now what we need to do is, whenever something like this happens, you would have learned already your conservation of momentum. What does conservation of momentum tell you? You have an object here, you have another object here. This is at rest. This is mass M. Let us say this is capital M. When this goes and hits here, so what will happen? This object will now start moving with a different velocity v dash because the masses are different. Now, can I apply here? What is the condition for conservation of momentum? Condition for conservation of momentum is no force should be applied, no external force. Of course, see, when I say this is moving at the velocity here, force is not applied because it's a frictionless table. If at any two instants you find out the velocity remains a constant. When you say velocity is constant, that means no force has been applied, right? Okay, so it moves to the same velocity and hits it. So you can definitely apply over here. Let us apply it first. M into V is equal to capital M into V dash, which means once this mass comes and hits it over here, this object would be moving with a velocity V dash. V dash is equal to mv divided by capital M. Okay, the first part of it we have come to know. What is the velocity of the rod when it moves? But what is required? The required thing is that find the distance traveled by the center of the rod. By what distance that the rod travels. Now you see, I have a rod. Now this is now, after this particle hits it, it starts moving at a velocity v dash over here. Will it stop? It won't stop. Why it doesn't stop? Because there's no friction. If there is a friction, somebody will stop it, right? The friction will be able to stop it. If there is no friction, it keeps on continuing to move, right? Now, if I ask you, after t seconds, where is the rod? Or what is the distance traveled with the rod? What's your answer? The answer is, you will just say v dash into t is equal to s, right? Wow. Now see, what has been asked? Find the distance traveled by the center of the rod by the time it turns to an right angle. Okay, so somewhere we have to incorporate this. And finally, you need to get this expression. Now look at this, there's a t here. V dash you already determined, but I do not know what's the value of t. Which means I have this rod, you applied a velocity here. You gave this a push. Okay, not a push, sorry. So this came and hit it over here. It transferred all its kinetic energy. After some time, this rod went to this position. This rod went to this position. Now the question is, how much time does it take to start from here and to go here? If you know this, then definitely this is not difficult. You can easily find out, right? The time required by the rod to complete 90 degrees. That's what you need to know. Now, how do we do it? Okay, good question, right? So at least we got a clue as to what to be done. Now what we do is, let us apply conservation of angular momentum. Why conservation of angular momentum? See, I am giving a velocity, a kinetic energy to it. I am not giving it a torque. What is a torque? A force that has been applied on a rod perpendicular to a distance, perpendicular distance. So therefore, there is no force being applied. So now what we do is we can apply your COAM. And when I take your COAM, what do we have here? COAM tells you that the initial angular momentum is equal to final angular momentum. Li is equal to Lf. Now let us find out what is Li. Li is nothing but equal to, if I consider, now I should choose one point over here. Which point I will choose? I will choose the center of the rod as a point. Okay, because there's no torque being applied. That's what I will consider. As a result of it, I will write mv into, what is this now? L by 2. Why L by 2? Because you see, this length is L by 2 over here, and the mass comes nearby to it. Okay, when it hits it here, what is your angular momentum? Just 1 nanometer before it hits it. Okay, what is your angular momentum? So therefore, this is Li. Now let us write Lf, final angular momentum. Now because of this mass coming and hitting the rod, now what will happen is there is a rotation being seen. Not pure rotation. It's not pure rolling. Okay, partly it has been rolling. Okay, so what I will do is I will write moment of inertia I multiplied by omega. Now what is this moment of inertia? Moment of inertia of the rod about the center. Because here also we look at center. So we'll look at center only here. So this should be ml square divided by 12 into omega. You have got this. Now what does your COAM tell you? COAM tells you that this Li is equal to Lf. Which means let me equate these two, which will now be equal to mvl divided by 2 is equal to capital ML square divided by 12 into omega. You can ask me, hey, why should I do all these things, right? Just wait for a moment, you will get to it. Now, ln cancel, 2 1s are 2 6 are. So what do we have here? We have omega. Omega should now be equal to 6mv divided by capital M into L, right? So now, if you notice this equation, M into V divided by capital M is nothing but V dash. Because why I want to transform this is because this V is a velocity of the particle, but I don't need that velocity. I need this small V dash over here. Okay, so what I will do is I will convert this as mv divided by capital M, mv divided by capital M. This part of it is already known to me as the V dash, as V dash from here. So I substitute that value 6V dash divided by L. What next? So where we have come and stuck over there. We need to know what next. Now we know omega is equal to theta by t. Right? What is theta? Theta is pi by 2. What is time? Time is t here. Why do I have to put theta equal to pi by 2? Because you had the rod like this and it started moving like this. Describe the right angle, which means the angle there, the angular displacement is pi by 2. So I get the answer here as pi divided by 2t. Right? Now, in other words, what do we have here? Now I need the value of t somewhere. Okay. Now I know omega equal to 6V dash by L from the previous expression. 6V dash by L is equal to pi divided by 2t. T should now be equal to 12V dash. T should be equal to, I'm sorry, T should be equal to pi L divided by 12V dash. You got this also. What's the next step? Next step is quite easy because we are only worried about this time t here, right? Let us plug in this value here. So distance moved by the rod because of this one is nothing but S is equal to V dash into t, right? Which is V dash multiplied by what is t here? T is pi L divided by 12V dash. Wow, see, this also goes away. Thus I get the answer as pi by 12 times L. S is equal to pi by 12 times L is nothing but the distance traveled by the rod when the rod makes an angle of 90 degrees with respect to the horizontal. Okay, I hope you would like this problem, and maybe once or twice you need to look into this problem into detail so that you get a complete hand holding on this problem. Okay, this problem has several concepts, But how do you string those concepts? This is very important. Okay. Thank you, friends, for watching this video until the end. And if you really like this video, do share and subscribe to my channel for more updates. Thank you, and thank you very much.